Good morning. This video is designed to help you get started with problem set number 3. And I want to start by reminding you about the glorious mineral zircon, which is zirconium, silicon, oxygen. And uranium is quite incompatible in most elements, but it is fairly happy in zircon because it substitutes for the zirconium. And there are two isotopes of uranium that we're interested in because they are radioactive, and that is the uranium-238 and the uranium-235. These both decay to lead, to lead-207 and lead-206. Alright, so what I want to do today is I want to remind you that how important the ratios are here and not the ppm or the concentration. So let's say that you have some kind of granitic rock that's forming from some melt, okay? That's supposed to represent the melt. And there'll be these small little zircons that are forming as accessory minerals, small 200 to 300 microns in size, much smaller than the quartz and feldspar crystals and biotite crystals that you find in the granite. Anyway, so these minerals are forming, and if they're all cooling at the same time, they should all have the same age. But what they will not have is they won't have the same concentrations of uranium. So let's say to start with, we have uranium atoms in this crystal right here, and there are lots of them. And then in this one, there's only a few. And this one, there's even less. When time goes on and those uranium atoms decay to lead, at, let's say, one half-life goes by, we'll have then half of those little blue dots, red dots, will change to blue dots. So even though the concentrations of uranium and lead are not the same in all three of these crystals, the ratio of uranium to lead will be the same because the same amount of time has passed. And to add sort of one more complication, but it turns out to be an excellent complication, is that it's not just uranium in here. We have uranium-238 and uranium-235, which decay to different isotopes of lead. So even though three different minerals in one rock will have different concentrations of uranium and lead, the ratios will be the same because the same amount of time has passed. This is the age equation, and so we can rewrite this using both pairs of uranium and lead. We can use our uranium-238 that decays to lead-206. And we can also write this equation for uranium-235, which decays to lead-207. So if you have one rock with many zircons in it, and I'm just going to draw 4 for right now, and even though the concentrations of uranium and lead will be slightly different in all 4 of these crystals, if they all formed at the same time, they should have the same ratios of lead-206 to uranium-238 and the same ratios of lead-207 to uranium-235. Now, of course, there'll be some natural variability, such as complications with common lead or lead loss, or the mass spectrometer making measurements that are not quite right. So what we do is we get as many mineral crystals as we can, and what we're going to do is we calculate the 238-207 age. So what we do is we plug in the daughter to parent ratio that we measure, and we plug in the decay rate right here. So we know this, we're going to assume this is 0 for the problem set, and we know this. So then what we can do is we can calculate time. So we can calculate the time, and we call that for doing the 238-206 ratios, we're going to call that the 238-206 age. So 238-206 age. And that is basically the time that you get when you plug in the 238-206 ratios that are measured in the paper. And then you can also do this for the 235-207 system. So we call that the 235-207 age. And in theory, these ages should be the same, or at least really, really close. So what you have in your problem set is a data table, and we're just working with the Ironside Mountain Batholith. So there are 4 rows of data for the Ironside Mountain Batholith, which we'll just call IR. So what you're going to do is you're going to generate 8 ages. These 4 rows, each one of these corresponds to 4 different minerals, like I've drawn here, like this. And each of those minerals yields those ratios in the chart. And each of those ratios can be calculated for a 238-206 age and a 235-207 age. So when you do that, you'll enter in your in the data table that I have on the problem set. So there's 4 of them, and what you're going to do is you're going to put in the age, the 238-206 age, and the 235-207 age. All right, so how are you going to make those calculations? Well, you're going to be working with the decay equation. And I also suggest that you go in the reading and look at equation 3.1 and equation 3.2 to find what you're going to plug in to solve for T age. All right, let me know if you have any questions. And the next thing that I'm going to show you is the Concordia plot. So you remember this from lecture. And the next video is going to show you how to do this in Excel. But basically for problem 2, what you're going to be doing is generating this curve. And so what I've done is I've made this Excel sheet that you'll need to download. And what it has on it are a series of time steps. And so remember that where you are on this curve tells you how much time has passed. So let's say that we have some zircons that are forming today, and since they only incorporate uranium in them and no lead when they initially form, it would only have uranium and they would have no lead at all because no time has passed, so no lead has accumulated in the closed system in the zircon because there hasn't been time that's passed. So that would plot down here at 0 times 0, and the ratios would be 0 because there's no lead at all. So the lead 207 and the lead 206 values are 0. Now as time passes, so let's say 500 million years pass, so that's 500 million years, what we see is that the ratio of 206 to 238 and 207 to 235 has started to increase. And that's because there's more parent decaying to daughter. Parent is decaying to daughter, increasing those ratios. Let's say 1 billion years goes by, and you can see that the ratios are increasing because daughter is accumulating and we're losing parent in our little, in our grain. So we're going to start accumulating the lead. All right, now the decay rates are a little bit different. You remember that the half-life of 238 uranium, the half-life is something like 4.47 billion years. And the half-life for the other system is something like 700 million years, 703, something like that, million years. And so that explains why this curve looks the way it does. So what we're going to do is we're going to be accumulating daughter faster here, which is why at, let's see, 3 billion years, the ratio of 207 to 238 is 20 times, whereas the ratio of 206 to 238 is only 0.6. And that's because that daughter is accumulating much slower. So anyway, go check out the other video for the Excel video on how to actually make this plot in Excel, and make sure to download the time steps on the Excel file in Canvas as well. Good luck.